Hi everyone. In the previous video that you looked at, we were introduced to graphing cubic functions in general. You had a look at the base function and a little bit about end behavior of that function. In this video, we're going to have a look at transformations. So first of all, there we go. There's the base function. The gradient is quite steep, and as it approaches x equals 0, it gets flatter and flatter and flatter and hits x equals 0, y equals 0 here, where it doesn't change direction. It keeps on going up, but it starts slow and then gets fast again and faster and faster. So because of this, it's still a turning point, but we also call it an inflection, because instead of changing direction, being a maximum or a minimum value here, instead it just notes the point where it stops being slow and starts getting fast again. Okay, anyway, that's enough of that. Let's have a look at transformations. So, base function, we just saw it. Here's the new and improved transformed function. Now I say it's an improved function. Okay, it's a new function. Let's put it like that. Let's have a look at it. Looks familiar? I hope it does. It should look very similar to your turning point form in quadratics, except we've got this big old cube here, and that cube makes a difference, obviously, to what the graph is going to have a look at. But same idea. It's the just like f of x equals x squared was the base quadratic, which then got moved all over the place when it was transformed. Similarly, the base function for this general form here is a cubic, which moves all over the place. Okay, so we need to remember, I guess, what that does, and what that does to the function. So I'll give you a moment to have a look at that and maybe consider what those values do to the base function in case you've forgotten. So you might want to pause the video. Okay, assuming you paused the video, hopefully you've had a chance to think about it, but here they are. These are vertical translations or vertical shifts. Just giving you different language there because you will come across both. The H here is called a horizontal shift or translation, and the A here is a dilation. It either stretches the graph away from the y-axis or it compresses it towards the y-axis. If it compresses if a is a number bigger than 1, or if it's a fraction, then it stretches it. And I should also say, of course, if a is less than 0, it also acts as a reflection. And just a reminder that a reflection means that the graph flips over the other way. We say it is reflected about the x-axis. Okay, so there's the x-axis, flips that way. Okay, so that's it in a nutshell. So we have a look at an example so you can sort of see that in action. How about this one? Sketch f of x equals -3 outside of x plus 2 or cube plus 3. Let's think about it in terms of those transformations to start with. We have the -3 there. So that -3, what does it do? Well, first of all, the fact that it's 3 will mean that it stretches. Or does it? No, it compresses, doesn't it? Let's get it right, Richard. It compresses the graph by a factor of 3. And I should say towards the y-axis, but I'm just not going to for time's sake. And the negative means that it is reflected. And I'm not going to write about the x-axis. Okay, so it's compressed and reflected. The plus 2. Okay, if you remember, I'll just quickly switch over to the other one. If you remember that the form is x minus h, so in x plus 2, I've got x minus -2. And so if you think about it like that, the negative, that's actually a -2. So it goes to the left. Okay, so It's a horizontal shift or horizontal translation, 2 units left, and the +3 at the end there. So we've done that one, Now we're looking at +3. The +3 is a vertical shift or a vertical translation, 3 units up. Okay, so they're the critical pieces of information. So if you remember what the base graph looks like, which is going up, gets to 0, and then goes up again like that. If that's the base graph, using these bits of information here, you should be able to figure out what that graph looks like. You might want to take a moment to pause the video again, just think about it, or even draw a rough sketch without worrying about critical points. Just draw a rough sketch as to where you think the graph would be and what it roughly would look like. Very useful to do that, I think. Okay, moment to pause. Okay, so let's have a look at it on Desmos so you get a bit of a feel for it. And then after that, I'll show you how to go through the process of working it out. So under Desmos here, here's our base graph. I'm going to leave it there so you can sort of see how it relates to it. Let me just bring open that left-hand panel there. You might want to do this yourself if you so wish. We're going to start off by just resetting these values back to 1, back to their basic values. So by setting a equal to 1, it's basically like that a disappears. If I set k equal to 0, now that bit disappears because +0 doesn't do anything. And if I set h equal to 0, that's now just x cubed there. So if I now make that visible, there we go. It's right on top, like so. So I'll leave a till last. Let's have a look at changing the value of k. So it says go up 3 units, so 1, 2, 3 units, and as you'd expect, 1, 2, 3 units up. And then we shall change h. Now, it was x plus 2 or cubed, but don't forget that if I make h equal to 2 here, you can see it's gone over to the right, but don't forget I've just subtracted 2. So that would be x minus 2. I want x plus 2, so I have to subtract -2. So I've deliberately this time gone the wrong way. So I'll go back to 0, and now I'll go to the left 2 units, 1, 2. There we go. So when h equals -2, that's x minus -2, or x plus 2 all cubed. And hence, the inflection, which was at 0, 0, is now here at -2, 3. Okay, so it's basically just shifted this way. But we also did have a value for a, didn't we? Now, if I make a equal to +3, just so you can sort of see the compression happening, there we go. You can sort of see the graph is squishing up a fair bit there. But if I instead go to -3, it'll be the same squishiness, same compressed graph, but it'll be reflected. So bring it back to regular old size, and then go to 0, which a can't be equal to 0 because, as you can see, it flatlines it. But then if I go to -1, there we go. So +1, -1, we have the graph reflected upside down, so reflected about the x-axis, and now I'll go to -3. So a bit more of a squishy graph, and it's going down and then down more as opposed to up and then up more. So that's basically what it looks like. But now let's go back and see how to actually process that. So again, assuming you didn't have a graphics calculator or didn't have Desmos, how would you go about sketching it? So unsurprisingly, I hope by now, it's the same kind of process in that we look for critical points. So number 1, what's the turning point, or in this case, the inflection? Number 2, where are the y-intercepts? Number 3, or y-intercept. Number 3, where are the x-intercepts, if there are any? So let's go for turning point first. I'm using the turning point first because it's easy. Okay, so the turning point is an inflection. Okay, so whenever you have a graph, whenever you have it in this form, you know that it's going to be an inflection as opposed to a turning point. We'll speak more about that in the next video. But the turning point is effectively HK. And sometimes I've heard people say we're going to HK that graph, and that's what it means. It means we're going to take the base function and just move it to wherever HK is. So again, just don't forget that that plus 2 becomes a minus negative 2, and so HK is negative 2, 3. Okay, so that's it for the turning point. Number 2 is the y-intercept. Now I'm going to zoom up a little bit on this screen just so I can fit all the calculations onto this one screen. So it's going to look a bit bigger, but then I'm going to write a bit smaller. Okay, so the y-intercept is when we let x equal 0. So we take the function and we set it equal to 0. So that's a different notation there. Okay, so y is equal to f of 0, and that is negative 3 outside of 0 plus 2 all cubed plus 3. Okay, I reckon we can do this in a couple of steps. So 0 plus 2 is 2, 2 cubed is 8, 8 times negative 3 is negative 24. And then I've got a plus 3 here, which gets us to negative 21. And so the y-intercept is when x is equal to 0, y equals negative 21. Just note, I think, that it is a rather large value, given that we were just at x equals 0. So remember that because it is a cubic, values are going to increase rather rapidly compared to a squared graph, quadratic graph. So yeah, negative 21 is quite a leap down. And then I'm going to zoom up again just so we can do the x-intercepts. Number 3, the x-intercepts, and we let y equal to 0. So we have negative 3 outside of x plus 2 all cubed plus 3 is equal to 0. I've just switched the left and the right over so that the x ends up being on the left-hand side. It's just for the sake of doing it. So we use a similar method to where we solve for x in turning point form for quadratics. Basically, first, we'll take 3 away from both sides. Taking 3 away to get rid of the 3 on the left means that we take 3 away from the right to keep it balanced. So we've got that. Divide both sides by negative 3. And that leaves us with x plus 2 all cubed is equal to positive 1. Negative divided by negative is a positive. Okay, and then we're going to take the cube root of both sides. So I'll just do that in blue so you can sort of see. So that's, we put a little 3 inside there to say it's not something times something, it's something times something times something would be the cube root of it. So when you have x plus 2 all cubed, that would just be x plus 2, so that's okay. Now in the quadratic form, if I'm taking the square root of 1, the result would be positive or negative 1, because minus 1 squared is 1 and positive 1 squared is 1. But for a cubic, it's different, because minus 1 times minus 1 times minus 1 is negative 1. So it's 3 negatives in a row that will make the result negative. And so the only solution to the cube root of 1 is in fact 1. So just the one value there. And then take 2 away from both sides, and I get x is equal to negative 1. And that gets me my second or third critical point, negative 1, comma, oops, wrong way around. So no, that's right, negative 1, comma 0. So I'll just zoom out now so you can see those 3 critical points. I'll just put them in red there so you can see them. We've got in decreasing size, but not decreasing importance, we have negative 2, comma 3 for the turning point. That's the point of inflection. We have 0, negative 21 for the y-intercept, and negative 1, 0. Now, just to keep it all on the same page, I might even just square off here. It's going to be a bit tiny, but we'll survive. And we'll zoom up into this area. And I'm going to draw my graph. Now, I know I need to go all the way down to minus 21, but I don't have to go that high up. So I think I might just draw my axes with the x-axis just cutting up the top here. I'm definitely not going to get it in the right scale, but I'm going to do my best to make it look at least halfway decent. So my critical point is 0, -21 for the y-intercept. So I'll stick -21 there. And it was -1, 0 for the x-intercept. So that's -1 there. And the other point, which we can't see on the screen there, is -2, 3 for the turning point. So -2 is, let's say there, and then 3 is about there, like so. So there's my critical points that I have labeled there. Sometimes you'll see the actual points labeled on a sketch, or it might be just on the axis like I've got here. So sometimes the actual point will be labeled with the coordinates, or it could be just the bits on the axes themselves. Okay, let's draw it. I'll draw it in red so that we can see it. So we know it's been reflected, so it's going to go down instead of up. So it kind of reaches this point here. So I'm going to start off with the inflection, and there it is there. And then it's going to reverse course and come back down again to -1. So there's that bit of it. And then this is where it's going to be tricky to get. So I haven't done a great job on that one. Should have been, certainly shouldn't have been wobbling like I've got here, but you know, it's roughly okay. It sort of shows there's an inflection and then cuts through there and goes down to -21. It's really hard to graph it if you don't have it to scale, and so that's okay though. It gives me a sense of what the graph is going to be looking at. Let's have a look at Desmos, and we'll see that what I've done here is roughly right. Okay, so if I'll just zoom out a bit so you can see that. Here we go. So -21's down here, inflection here, and away we go. So that's basically it for transformations. It's just a matter of if you can see a transformation, if the cubic is in transformed form, like so, then you know what you're looking for there. Now, I should point out before I finish the video, and this leads on to the next video, that not all cubics can be drawn, or can be written, sorry, in cubic form, in transformed form. So with a quadratic, you could say all quadratics could be written in turning point form, not so for a cubic. Okay, so when it can be written in cubic form, great. Then you can just use the transformations to draw it. But otherwise, you're going to have to do a little bit more work. I'll just show you an example of that, and we'll leave the video there. So this was a similar example to what was given in the first video, that one there, and you can see that instead of just being an inflection, it actually goes up, does change direction, down, then goes up. So it's kind of like the inflection here has been stretched out here, so it's got a definite change in direction of the gradient there. So that would not fit into turning point form or a transformed form. And similarly, here's another one in intercept form here. We've got 3 factors here. And if I show you what that looks like and zoom out, you can see that it's quite down and up and down. So it's quite the roller coaster ride there. Anyway, that's enough for this lesson. That will do for us. And next video, we will go through one of those intercept forms and demonstrate how to go from an intercept form to drawing the graph. Thanks for listening and watching. Bye.